So this is where the class sort of comes full circle. Do you remember way back at the beginning of the semester we talked about kinetics? Remember that? Rate constants? Well, you're kind of still in that because you're still working on that formal report, right? It's kinetics. Okay, so we're going to look at the kinetics of radioactive decay. So radioactivity is natural. We didn't make this up. It's not caused by something that humans have done. It's natural. All of the elements that have more than 83 protons and some that are smaller are going to be unstable. And many of these are naturally occurring. So bismuth is the last stable one, and then you've got 1, 2, 3, 4, 5, 6, 7, 8, 9. There's 9 elements there that are naturally occurring that have no stable isotopes. They are all radioactive. The reason that we still have radioactive nuclides is because new ones are constantly being formed, and many of the existing ones decay extremely slowly. So radioactive decay always occurs via first order kinetics. Remember, there was zero order and first order and second order. So we can write a very basic rate equation and say that the rate is equal to a constant times n. Here we're not looking at a concentration of substance or a partial pressure. We're looking at a number of nuclei. So the rate is going to be proportional to the number of nuclei. The more nuclei you have, the higher the rate. So some of these have very large rate constants and others have very small rate constants. Depends on the nuclide. So we talk about half-life as we did for kinetics of equations of reactions. So here we define half-life as the time it takes for 1/2 of the parent nuclides in that sample to decay to daughter nuclides. So after 1 half-life, half of the original sample has decayed. And because this is first order kinetics, we have this relationship that half-life is equal to 0.693 divided by the rate constant. So there's a direct relationship between the rate constant and the half-life. If you have a short half-life, you have a large rate constant. Long half-life, short rate constant. So the short half-life with a large rate constant, that's a reaction that occurs very quickly. Those nuclides are considered very active. They have a lot of decay events per unit of time. So if you're going to hold that Geiger counter near a sample with a short half-life, you're going to get a lot of clicks. If you hold it near a sample with a long half-life, same number of nuclides, you're not going to get very many clicks from that. Any questions about that? So thorium-232 has a long half-life, 14 billion years. So however you believe that the universe was, however you believe it came into being, there were thorium-232 atoms that occurred somehow. Now, there aren't necessarily new thorium-232 atoms being created, but because they decay so slowly, we still have them present. So the half-life means that if you started with 1 million of these atoms, after 14 billion years, you're going to have 500,000 left. After another 14 billion years, you have 250,000 left. So again, half-life means that every period you cut it in half. It's not a linear relationship. Sometimes we can get a little misguided in our thinking and say, well, half of it disappeared in 1 half-life, the other half will disappear in another half-life, and in 2 half-lives we have nothing. No, because every half-life you cut in half what you started with. And so we go to 1/2 and then to 1/4, and after another 14 billion years, we'll have 1/8 of a million. and then a 16th. It's not a linear relationship, it's exponential, and so it trails off over time. Radon 220 has a half-life of 1 minute, so a rather short half-life. So if you started with 1 million radon 220 atoms, you'd get down to 1,000 atoms in 10 minutes. So these decay very quickly. But again, it goes, if you have 1 million, after one half-life, you have 500,000. After another half-life, you have 250,000. Any questions? So here we have a graph, sort of like the graphs we saw back in chapter 14. Here, instead of concentration, we have number of atoms. Number of atoms of this nuclide as a factor of time, and we see that the decay is very rapid initially, and then it slows down. And so every time period, it gets cut in half. There's a table in your textbook showing some of the interesting nuclides and their half-lives, and also the type of decay that they undergo. And you see there's a tremendous variation in half-life. We've got the thorium up there with 14 billion years, and we've got a different isotope of thorium that's 1 microsecond for its half-life. So that stuff decays extremely quickly, right? All over the place. So with the first order chemical reaction, we can look at the integrated rate law, which gives us the concentration of reactant as a function of time. So we can take the natural log of the concentration at time t divided by the initial concentration, and that's equal to negative rate constant times t. For radioactive decay, instead of looking at a concentration, a molarity, we're going to look at number of nuclei. We don't care about the volume that they occupy. That doesn't matter. It's how many nuclei are there. So the natural log of the nuclei at time t divided by the number of nuclei initially equals negative kT. So we can do questions like this. Plutonium-236 is an alpha emitter with a half-life of 2.86 years. How long will it take for a 1.35 milligram sample of plutonium-236 to decay to 0.100 milligrams? So we're going to use that integrated rate law. The natural log of n at time t divided by n0 is equal to negative kT. So what we've been given here is a half-life. So T1 half is 2.86 years. We're not given a number of nuclei, we're given a mass. But the mass is directly proportional to the number of atoms, right? So since we're doing a ratio, if we converted milligrams into atoms on the numerator and the denominator, our conversion factors would cancel out. You guys okay with that? So we can actually look at the masses because it's proportional to the number of atoms. So for NT, we can use, that's at the current time, 0.100 milligrams. And 0 is what we started with, 1.35 milligrams. We're trying to find T, how long it will take, but we need the rate constant. How do we get that? The rate constant is related to the half-life. T1 half equals 0.693 over K. that's for a first order reaction? Well, we can just switch these. K up here and T1/2 down there. So calculating the rate constant is not a complicated process. So 0.693 divided by 2.86. It's important to include units. The unit there is years. So 0.693 divided by 2.86. I want to keep at least 3 significant figures. We've been really kind of sloppy with sig figs. It's always better to include too many rather than not enough. So that's, I think, what I should have, and I'm just going to put down two more. What's the unit on the rate constant? 1 over year, or a year to the -1. So that's our rate constant. So now we have everything we need to plug into this. We're trying to find t, the time. We've got the rate constant, and we've got nt and n0. So to rearrange this equation and solve for t, we're going to divide both sides by -k. So the time is going to be -1 over k, which is 0.24207 years, times the natural log of the amount at time t divided by the amount initially. We see that the units cancel out there. We've got natural log of 0.1 divided by 1.35, and that's going to be divided by -0.24207. So that's plenty of numbers to write down. What's the unit on that? Years. Because here we're dividing by 1 over year, and so that gives us year as our unit of time. So it would probably be appropriate to round this to 3 significant figures and call this 10.8 years. Any questions? So the mass is directly proportional to the number of nuclei. The integrated rate law has a ratio in it, and so we can substitute masses for numbers of nuclei, and I did that already in the previous problem. We also see that the rate of decay is directly proportional to the number of nuclei and can also be used in the integrated rate law. Because remember that the rate is equal to the rate constant times n. The rate constant is constant, it doesn't change. So if we say the rate at time t, that would be equal to the rate constant times n at time t. The initial rate, rate 0, equals the same rate constant times n0. And so rate t over rate 0 equals k nt over k n0. The k's cancel out, and the ratio of the rates is the same as the ratio of the numbers of atoms. which is also the same as the ratio of the masses. Any questions? Radioactivity can be used to date artifacts. Fossils are things that were living at one time, and artifacts are things that were just, stuff people made. So radiometric dating uses the predictable decay of radioactive isotopes in the environment to estimate the age of rocks or artifacts that have those isotopes in them. Radiocarbon dating specifically is looking at the decay of carbon. This was devised in 1949 by William Libby, the University of Chicago, and it makes use of a radioactive signature that results from the presence of carbon-14 in the environment. And Libby got the Nobel Prize in 1960 for this. So radiocarbon dating is used by archaeologists, geologists, anthropologists, and other scientists to estimate the age of something that was alive at one point that has carbon in it. Here's an image of the Dead Sea Scrolls. These were found in 1947 by some shepherds. They were looking for a lost goat, and they went into a cave near the Dead Sea and found some jars with ancient scrolls stuffed into them. And this is like, one of those cool things that happens in a movie, right? So you look at these scrolls, they're obviously very old, but how can you tell how old they are? Well, 1947, that was before they had discovered radiocarbon dating. But then Libby came along and was able to discover that. And so the age of the scrolls was determined by looking at the amount of radioactive carbon remaining in the scrolls. And so these are estimated to be about 2,000 years old, and these are older than any other copies of the Hebrew Bible by about 1,000 years. So that was a big, big discovery. And of course, there's a big problem with these archaeological artifacts that people try to fake things, right? Because, I could say I discovered this, it's really, really old, and I could sell it or get famous or something. And so you always have to look out for people trying to pull one over on you. So how does radiocarbon dating work? Well, carbon-14 is an isotope of carbon, and it's constantly being formed in the upper atmosphere. In the upper atmosphere, you have a lot of neutron bombardment from you got a lot of energy from the sun up there. And when nitrogen-14 is bombarded with a neutron, it can make carbon-14 and a hydrogen atom. The carbon-14 is radioactive, and it decays back to nitrogen through beta emission, and it has a half-life of 5,730 years. Bless you. So carbon-14 is constantly being formed in the atmosphere, and it's also decaying back to the thing it was formed from. It was just kind of going in a circle up there. Because it's continuously formed and continuously decaying, the equilibrium amount of atmospheric carbon-14 is nearly constant. It varies a little bit, but it's not too significant. So there's atmospheric carbon-14 that can become oxidized and form carbon dioxide, where the carbon atom is carbon-14. Carbon dioxide is taken in by plants through photosynthesis, incorporated into the plants. Animals eat the plants. The carbon-14 makes its way up through the food chain. The result is that all living organisms, you included, contain the same ratio of carbon-14 to carbon-12 as that which is found in the atmosphere. Most of the carbon in the atmosphere and in your body is carbon-12, but a little bit of it's carbon-14. And you can measure the ratio of carbon-14 to carbon-12. As long as the organism is alive, it will continually recycle the carbon, and so it will stay at the same ratio of carbon-14 to carbon-12. When the organism dies, it stops incorporating new carbon-14. The carbon-14 that was in the organism when it died remains there, but it decays. So after, 5,715, I think they updated the half-life of carbon-14. They used to say 5,730, and you'll still see that a lot of places, like in the previous slide, and in the worksheet, but I believe this is the new, most up-to-date version. The carbon-14 decreases with a half-life of 5,715 years. So if the organism died 5,715 years ago, the ratio of carbon-14 to carbon-12 will be half what it is in living organisms. And so you can say, hey, well, this is like, 5,700 years old. Any questions? So there's a limit to the age that can be estimated. The maximum age is around 50,000 years, because after 50,000 years, that's so many half-lives that the amount of carbon-14 still present in that object is undetectable. And so then you can't look at the ratio of 14 to 12. Too low to accurately measure. So we can check the accuracy of the radiocarbon dating by comparing it to objects whose ages are known from historical sources. So, this might be an Egyptian mummy, or it could be a tree. Trees' ages can be identified by counting the number of rings in their trunks. So we do see a deviation of up to 5% due to variations in atmospheric carbon-14 levels. You can use western bristlecone pine trees to make corrections for the amount of carbon-14 at those different times. It's really, really kind of cool. Okay, so a researcher claims that an ancient scroll originated from Greek scholars in about 500 BC. A measure of its carbon-14 decay gives a value that is 89% of that found in living organisms. How old is the scroll, and could it be authentic? So the number we're given here is 89%. So the rate of decay is 89% of that found in living organisms. Remember that a percentage is a part times a whole over 100, or it's 89 parts per 100 parts. So currently it's at a level of 89, when initially it was at a level of 100. So 89 is our rate at time t, and 100 is our rate at time 0. We don't need to have any units in there. You could look at this as numbers of atoms. You could look at it as masses of carbon-14 to carbon-12. You can look at it as rate of decay. It all ends up being the same. Rate t over rate 0 is 89 over 100. So we have that relationship that the natural log of rate t over rate 0 is equal to negative kt. But we need k, the rate constant. So for these first order processes, the rate constant is equal to 0.693 divided by the half-life. So let's use the more modern half-life, more up-to-date. 5,700 and, was it 14? 15 years. So again, we can take this and express this as negative 1 over k natural log rate t over rate 0. Instead of dividing here and writing down the value, I'm going to divide by k. I could just take this expression for k and invert it and stick it in there and just do all the math at one time. So 5,715 years over 0.693 times the natural log of 89 over 100. Negative 5,715 divided by 0.693 times the natural log of 0.89. $961 years. That's an estimate of how old this scroll is. We can use radiocarbon dating on a scroll because it was probably made out of papyrus, which is a plant, right? You can also date paper because paper is made out of trees that were plants, right? You couldn't use radiocarbon dating on stone tablets, right? So if you claim to have found the 10 Commandments on the stone tablets, radiocarbon dating is not going to work on those. So any questions about how I got 961 years? Okay, so we have a number, but that's not the answer. Could it be authentic? Well, if they're saying that it's from 500 BC, how old is it then? Well, what year is it? It's 2019. 2019 plus 500. So 2,519 years is what they're claiming. It's old, but it's not that old. So it's this many years old. It's not authentic. It's not what they're claiming it to be. Any questions? So radiocarbon dating only works for things that were once alive, and it only works for things that are less than 50,000 years old. We can also use the ratio of uranium-238 to lead-206 in rocks to date things that were not alive. So igneous rocks have uranium in them. The uranium decays to lead-206, and that is a measure of time since the rock solidified. So uranium-238 decays to lead-206 with a half-life of 4.5 times 10 to the 9th years. This is a much longer half-life than the carbon-14, and so this can be used to measure much longer periods of time. So one of the issues here, though, is how do you know how much uranium-238 was initially present in the rock? Because the amount of lead-206 would be related to the amount initially present, and we don't know what that is. But when we look at the lead that occurs from radioactive decay, it has a different isotopic composition than lead that may have been initially deposited in the rocks when they were formed. So when that rock solidified, there was probably some lead-206 in there, well, some lead in there, in addition to the uranium. And so we can look at the difference in the the isotopic composition and figure out how much uranium has decayed.